Hello everyone, this is Dr. Webb, and welcome to the next video for Math 235. So in the last video, we introduced the notion of the derivative, and we took a very geometric viewpoint of it. That the derivative is used to solve this old question that dates back all the way to ancient Greece and perhaps before, about how to find tangent lines to curves. But when the derivative was actually developed by Isaac Newton in the 17th century, he was not really trying to solve geometric problems so much as he was really trying to use the derivative to solve real-world problems. And so in this video, we're going to look at how to view the derivative in terms of more of a real-life setting, in terms of functions dealing with things in real life. Okay, and so going back to what we saw in the last video, this is using this geometric interpretation. What the derivative of the function is at some point x equals a is it's the limit of these secant slopes. Right? So each of these, this is the slope of the secant line between the point A, f of A, and some point x, f of x. Clean that up a little bit. And when we take the limit of these secant lines as we bring these 2 points closer together, so in particular we're leaving the point AF of A fixed and bringing XF of X closer and closer to it, well, we take the limit of these slopes, we get a value, and that value, that F prime of A, is going to be the slope of the tangent line. So this is the geometric viewpoint. We're thinking about this function representing a curve on a graph, and then we're doing this very geometric construction of drawing lines between points on the graph, and then imagining what happens as we bring those points closer and closer together to get the tangent line, to get the slope of the tangent line. Okay. Now let's try and think about how we can reconstruct this, but in a much more real-world setting. So let's suppose that we have some function, m of t, and let's say that it gives us the total mass of a compound that's produced by a chemical reaction, where t is in terms of hours, and the units of our function is grams. And so let's think about what each of the following represent. Okay, so what if I said m of 2 equals 175, right? So 2 is getting placed in to t, and this is the 175. This is talking about a value of the function. Okay, and so we are plugging in 2 hours, and we're getting out 175 out of the function. And so this is saying that after 2 hours, 175 represents the mass in grams of the compound that's been produced. So after 2 hours, 175 grams of the compound has been produced. Okay, what if we looked at m of t2 minus m of t1? Right, so t2 and t1, these represent 2 different times. So we've plugged 2 different times into our function, and then we're taking the difference between them. Well, if we're taking the difference between them at 2 different times, we're really looking at how much the value of the function has changed between those 2 times. So m of t2 minus m of t1, this is talking about the change in the mass of the compound produced between time t1 and time t2. And again, the units here would be in grams. And as shorthand for this in math, we often use, instead of saying change of, we might start using this capital delta. And so this stands in for meaning change in. And so if we're taking the difference of the function between 2 points, we're looking at the change of the function. We're looking at the change of the mass, in this case, between those 2 points. And so we might say delta m is equal to the difference of m at t2 minus t1. Okay, now what if we then took that difference and then divided by the 2 times? Right, so we're looking at the top here is again talking about the change in mass, but now then we're dividing by the change in time between those. Well, this is an average. Right, so this is looking at the average rate of change in the mass of the compound produced between time t1 and time t2, and the units of this, the units of the top are in grams, the units of the bottom in this case is in hours, so when we divide them, our units are going to be grams per hour. And just as before, when we talk about the top, we said this is the change in m. Well, when we're taking the difference of the 2 times, we can think about that as being delta t. And so this average rate of change sometimes is shorthand. We might represent it as delta m divided by delta t. To get an average rate of change, you would take the change in the function divided by the change in time. What's important to note here is that this formula for average rate of change, this is the same formula as slope. And so this is where we're going to get our connections in to derivatives. So this average rate of change, this is going to be playing the role of our secant slopes. Okay, so we saw we had delta m divided by delta t. This is our average rate of change, and it is the change in the masses divided by the change in times. And now we can talk about, same as we did with the secant slopes, what happens as we bring the 2 points together. Okay, so we're going to imagine keeping t1 fixed. So t1 is fixed, but t2 is going to be moving closer and closer to t1. And so we'll take the limit as t2 approaches t1 of our average. And now this looks, we are taking a limit of these average rates of change, and which looks exactly as the same formula as taking a limit of secant slopes. So this is same as a limit of secant slopes. And so what happens when we take this limit of secant slopes and move them closer together? That's when we get the derivative, right? And so this would, same as we saw before, the math behind this is the same. It's just we're no longer thinking about it geometrically. We're thinking about it in terms of real-world functions. And so this is the derivative of m at time t1. Okay. And, in terms of thinking about this, in terms of the delta notation, well, we're just replacing the delta m with the delta t, the same as we saw before. But what does it mean for t2 to go to t1? Well, we're really talking about that change in time getting smaller and smaller and going to 0. And so our t2 going to t1, that's getting transformed into thinking about delta t going to 0. Right. And so on this side, this limit right here, this is much more thinking about a limit of average rates of change. Rates of change as delta t goes to 0. Okay. And so in the geometric way of thinking, the derivative represented the slope of the tangent line. Now, if we're talking about an average rate of change as the change in time goes to 0, well, we're thinking about that change that's happening in, no change in time whatsoever. And so this gets the name instantaneous rate of change. So m prime of t1 represents what we call the instantaneous rate of change in the mass of the compound at t1. It is the rate things are changing just at that point. It is not an average. It is what's happening exactly at that point. So because we are taking the limit of things that are in grams per hour, that doesn't really change. The units of m prime will also be in grams per hour. And that's one thing to remember about the derivatives, especially when you're thinking about them as representing the instantaneous rate of change. These are always going to be the same as the units for average rate of change. Same units as for average rate of change. Okay, so let's bring in another function. Derivatives are used quite often to think about things like population. So let's let P of t represent the population of Harrisonburg in the year t. What do each of the following quantities represent? Okay, so what if we did P of 2015 minus P of 2005? Well, so this is a change in population, and it's a change in population from years 2005 to 2015. Okay. What then if we took that and divided by 10? Well, what's special about this 10 here? Well, this 10 is coming from thinking about 2015 minus 2005 gives us the 10. And so 10 this is the change between 2 years. And so that is our delta t. On top, we still have our change in population, our delta p. So this is delta p over delta t. And so this is talking about the average rate of change between years 2015 and 2005. Okay. Finally, what if we talked about the derivative of this population function at 2015? Well, so this would be the instantaneous rate of change in the population at year 2015. And the units here would be people per year. Okay, and so this is the change happening exactly at that year. It's not looking over a range of times. It has gotten it down to this is the rate that's happening right now. Okay. And so, going back to how would we get this value for the derivative of the population function? Well, P prime of T1, again, this would be the limit of the average rate of change. So the instantaneous rate of change is equal to the limit of the average rates of change as delta t goes to 0. Well, if we think about this as a limit, Well, limit means that this average rate of change, as delta t is getting smaller and smaller, is getting closer and closer to this one value, p prime of t1. Right? So the delta p over delta t is getting closer and closer to p prime. Well, that means that if delta t is small, these quantities are going to be very close to each other. That's what a limit means. So this is what the limit is saying. And so this really illustrates one of the most important functions, or one of the most important ways to think about and how derivatives are actually used practically, that over small changes of time, the value of the derivative and average rates of change are approximately the same. And so we often will use one for the other as an approximation. This happens an awful lot in the sciences. In fact, in the sciences, a lot of important formulas are what are called differential equations, which means they are equations involving derivatives of functions in some way. And sometimes it's actually very hard to get the values, the precise values of the derivatives. And so what do we do instead? We estimate it with using the average rate of change. On the other hand, sometimes we have very nice formulas that we can get derivatives out of, but what we really need are the average rates of change, and so we will use the derivatives to give us a good approximation of this average rate of change. And so sometimes we use one, sometimes we'll use the other, but they're not quite interchangeable, but they are good approximations for each other. Right? So the key point is that the average rate of change can be used to estimate the instantaneous rate of change. So that's using delta p over delta t to approximate p prime of t, and vice versa. And so we can go the other way as well. Okay, and so thinking in this way, if I multiply delta t to both sides, we get the derivative times delta t is about equal to the change in p. Well, if we unravel what the delta t and the delta p mean, well, delta t, we're really talking about change in time. So I'm thinking about t as being my variable, and we're keeping t1 fixed. And so delta t will be the difference between t and t1. And delta p will be the difference between p of t minus p of t1. And then if we move the p of t1 over, well, what do we get? Well, this function right here, this is an analog of the tangent line. So this is the equation for a tangent line. And so it's saying that we can use a tangent line to approximate the values of the function. Okay, and that is one of the important ways in which derivatives are used. They are used to get tangent lines to allow us to approximate the function. Okay, so this is, here's another example. And so in this table, we have water is leaving a tank. At time 0, the tank is starting off with 50 liters of water, but then after a couple minutes, water has been flowing out. And we want to approximate the instantaneous rate of water loss at 2 minutes. Okay, so let's say our function here, our volume, we got to name it something, so let's call it v of t, where t is talking about time. And so we want to know the instantaneous rate of water loss at 2 minutes. So the 2 minutes is talking about our t, or really our t1. And if we're talking about the instantaneous rate of water loss, what we want here is the value of the derivative at 2. Okay. Now what we have is a table of values, and so we don't have a nice function that we can apply a limit to. The best we can do is estimate it. Okay, and so we see that the top is in intervals of 2 minutes, and so we want to kind of figure out what the average rate of change is Well, really, the instantaneous rate of change at 2, and so we're going to use average rates of change to approximate it. Okay, and looking at this value, that we have a couple different choices to do it. So we're always going to be using the fact that delta V over delta T is going to be about equal to V prime of 2. But our choices come in how we can calculate this average rate of change. So on the one hand, we could use the values going between 2 and 4. Okay, and so we could say V of 4 minus V of 2 divided by 4 minus 2. And so V of 4 is 46.1 minus 48.4 all over 2. And so this is minus 2.3 over 2, which is going to be minus 1.15. And what are the units here? Well, the volume is in liters, denominator is in minutes. So this is in liters per minute. Okay, and so this is using the time going forward after 2. And so what this is called, the fancy name for this is called a forward difference approximation. The forward coming from, we're starting at the time we want and looking at what happens going forward from there. Okay. And so this gives us one approximation. Now, there's nothing special about doing from 2 to going forwards. We also could think about starting from 0 to 2. And so let's clear some space here. So we also could do the backwards difference approximation. And so we could use V of 0 minus V of 2 over 0 minus 2. And V of 0 is 50 minus 48.4 over 0 minus 2 gives me minus 2. And so this is going to be 1.6 divided by minus 2, which gives us minus 0.8. And again, this is in liters per minute. So this gives us a slightly smaller value. But this again is coming from, we're looking backwards in time and seeing what happened up until 2. And another important thing to notice here is that in both of these we've been getting negative values. Why is the negative value important here? Well, the negative here means that we are losing it, that we are not gaining the water is going out. So this is saying that the rate of change is negative means that it is a loss, as we have stated in the problem. Now, there's one other way to think about this, so let's clean this up again. Lastly, we could use what's called a central difference. This one's a little bit fancy. We're actually not going to use 2 at all. We're going to treat it as a point in the middle. And so this is a bit of a clever way of doing it. To approximate what's happening at 2, we actually look at the rate of change between 0 and 4. And so we look at the volume at 4 minus the volume at 0, and then do 4 minus 0. And so this would be 46.1 minus 50 divided by 4 gives me 3.9 divided by 4, and that is equal to 1.975, I believe, minus signs there. And again, this is in liters per minute. And And so what's interesting about this one, so again, this is called the central difference approximation, is that we're approximating the value of the derivative at 2, but we're not actually using the value at 2 at all. We're using values on either side of it. We're using values that put 2 in the center. And that's where the name central difference comes from. Okay, so in this problem, we were using the average rate of change to approximate the instantaneous rate of change. We're using the slopes, the secant slopes, to approximate our derivative, the tangent slope. Okay, now here's different question. So in this question, a rocket is lifting straight upwards. At 15 seconds, the rocket is 500 meters high, and its height is increasing at a rate of 70 meters per second. Estimate the height of the rocket at 20 seconds. So let's parse through what we have here. So we need a function. So again, t is going to be time, and we're talking about height. So let's let our function be h of t. It's talking about the height at time t. Now we have that at 15 seconds, the rocket is 500 meters high. So that's saying at time 15, the value of the height is 500. So h of 15 equals 500. Then it says, and its height is increasing at a rate of 70 meters per second. So at that particular time, at that instant, the rate of the increase in the height is 70 meters per second. So that 70 meters per second is talking about the derivative of the height at 15 seconds, and that its value is 70 meters per second. Now then the question is asking us, how can we estimate the height of the rocket at 20 seconds? So we want to estimate the value at h of 20. Now this is, the information we're given in this problem is completely the opposite of what we had in the last problem. Rather than being able to figure out, to estimate the derivative based on knowing the average rates of change, in this problem we're given the value of the derivative, and we need to go back and use that as an approximation for the average rate of change to get the value of h20. And so this is a time when we want to use our tangent line. So we'll actually call this the tangent approximation. And so just recall our tangent approximation is that the value of h of t, if we're using our time 15 as our reference, well, the slope of the line is going to be the derivative at 15. And then using our point slope form of the line, it's going to be t minus 15 plus the value of the height when t is equal to 15. Right? And so this is just the point slope form of a line for a line that has slope h prime of 15 and goes through the point 15 comma h of 15. Okay, and then we just get the plug in values here. So h prime of 15 is 70 times, we want to know what's happening at h of 20, so we're plugging 20 in for t, subtracting off 15, plus h of 15 is 500. Well, 20 minus 15, that's 5. 70 times 5 would be 350, and then we add the 500 onto that. And so our approximation for the height is 850 meters. And we actually can check through that the units here make sense. So what are the units of 70 for h prime? Well, it's a derivative, and so it's talking about meters per second. And so this is in meters per second. Now the difference in time, so it's time minus time, and so that's going to be in seconds. So meters per second times second, multiplying those two together, this 350 here is talking about just meters. 500 is also in meters. And so we have meters plus meters give us meters for our answer. That is all for this video. I will see you again soon.